Hi there, I'm Noah Kantrowitz. I'm an operations engineer at Geomagical Labs, and today we're going to talk about the GIL, containers, and how to make awesome infrastructure. Before we jump into the operations, let's lay out what the global interpreter lock actually is. When we talk about locks in this context, we mean a mutex. It's a value in memory that tracks which thread owns the lock. When two threads call lock.acquire at the same nanosecond, only one of them is going to get it. The GIL behaves like a traditional blocking acquire. If you try to get the lock and someone else has it, you wait until it's available. One slight complication is that the blocking wait has a timeout so that we can do something special if the GIL takes too long to acquire. So here's a representation of a running Python program. Boring, simple, single-threaded. The GIL is running here in the background, but because no other thread is trying to acquire it, we can just pretend it doesn't exist. So let's add a second thread to spice things up. In a perfect world, these would run concurrently and the output would be a garbled mess. But the GIL prevents two Python threads from running at the same time. So while both threads are running in parallel, only one of them can be making progress in a given moment. This means that we see it swapping back and forth, seemingly at random, but a single call to print can't be interrupted. You need the GIL in order to run Python code. Where does it come from? The simplest case is that the main thread starts with the GIL locked when Python loads, otherwise you wouldn't be able to run anything. But what about a different thread that wants to run? It'll need to acquire the GIL. This means blocking until the GIL is available, but there's a special case. After it's been waiting for more than 5 milliseconds, the requesting thread sets a global flag asking nicely for the GIL to be released, and then goes back to waiting. Once you have the GIL, you're running Python code, you eventually have to give it up so that some other threads get a chance to run. Anytime you make a potentially blocking syscall, Python automatically releases the GIL for you and then reacquires it afterwards. There's also that 5 millisecond interval check from before, which allows for a graceful handoff to a waiting thread that wants to run. A frequent example of that syscall behavior is making an HTTP request. Somewhere way deep down inside the library code, something is calling socket.receive, which is going to block until the response arrives. That could be quite a while in computer terms, so we automatically release the GIL while we wait. In this example, it's going to allow some prints to happen concurrently while waiting for the HTTP response. And as one less complication, I keep saying you need the GIL to run Python code because C extensions can do whatever they want. There's a bunch of macros and functions in libpython to release and acquire the GIL, just like Python does for the syscalls, but it's up to the extension author to use them correctly. All of this together gives us the 4 rules of the GIL. Only one thread running Python code at a given time, calling a potentially blocking syscall will release the GIL, do the call, and then acquire it again. After 5 milliseconds with the GIL, check if someone else wants it, and C extensions are a wildcard, they can do whatever they want. So that's the basics of the GIL. Plain scripts are nice, but when we're talking about production environments, we usually mean web applications. We'll talk about queue workers like Celery later, but let's look at the basic anatomy of a web server and figure out where it interacts with the GIL. A web server has 2 major components, the listener and the worker. The listener opens the socket, spawns some workers if needed, and then waits and monitors the whole thing. The worker accepts a new connection on that socket, reads in the request, runs some application code, and sends back a response. Doing that for one request at a time is relatively easy. Where things get fun is in how we handle multiple parallel requests. The most common worker model used in Python applications are multiple subprocesses. This avoids all GIL complications. Each request runs as the only thread in its process. When it needs to make a blocking call, it just blocks, and it lets the operating system worry about scheduling another process. The next simplest after that would be operating system threads, pthreads on Linux. Have one process with multiple threads, each handling one request. Other than that, it's pretty similar to process workers. When a thread wants to block, it just blocks, and it lets the operating system schedule another thread that's ready to run. Since the GIL is released in any blocking syscall, the main problem here is compute-heavy code. 2 parallel requests can't execute Python code concurrently. Green thread moves the complexity from the operating system and GIL into user space. The goal is to have code that it looks like it would with operating system threads, but under the hood it's actually all sharing a single thread in a cooperative manner. Rather than blocking on an operation that will take some time, the running application has to explicitly go to sleep and let another request run. The way this is implemented is that any syscall that would release the GIL now has to be monkey patched to instead suspend the green thread task and run another. Both gevent and eventlet automate this patching for common libraries, but anything that's not patched will block all tasks. Async code is similar to green threads, cooperatively sharing execution on a single thread, but instead of trying to make things transparent, it requires explicit code to handle the exchange of control, like async functions and awaitables. These can also be mixed and layered, like running multiple processes, each running multiple threads. This lets each model focus on the pieces that it's best at. These 4 options sit on a spectrum, trading resource usage for complexity. Spawning a new process is relatively slow and uses a lot of memory, but they provide a very simple operational model. Threads add some complexity, but they're much faster and smaller to create. Green threads or async tasks are entirely in user space and are so lightweight that they're usually created on demand rather than ahead of time in a pool. Worker queue or stream processing systems generally follow the same overall models. Rather than listening for an HTTP request on a socket, they instead listen on a queue or a database, but the request handoff and execution is similar. Celery in particular offers process thread and green thread concurrency implementations. Each of these four models has its strengths and weaknesses. From this point on, I'm going to mostly set aside async because most Python async frameworks are tied to a single web server, so there's not much to select there. The ASCII standard is trying to improve that, but things move slowly in standards world. This leaves us three main building blocks to play with. When running any production application, we need to think about redundancy and load balancing. In the container world, this means running multiple replicas across different physical hosts. This shares some characteristics with a process worker model. Rather than being forked off from the listener, instead, they'll be started from scratch. Unfortunately, this means they use the full amount of memory and are even slower to create, but on the plus side, it means that we get some baseline concurrency before we even start thinking about which web servers to use. The next task: which of these models should we use and how should we tune them? Let's talk about some common complications so we know which models could cause problems. The first stumbling block: health checks and socket back pressure. In any worker model using a fixed or capped number of workers, that also becomes the maximum number of parallel requests that can be handled. Most container systems support HTTP probes to know if a server is healthy, automatically taking the server out of the load balancer rotation if the probes fail. This allows for a degree of self-healing. If a server is overloaded with slow requests, it'll eventually be taken out of the load balancer rotation. It'll give it some time to finish its running requests, and then it'll go back into service. But with a worker model that allows an unlimited number of parallel tasks, like many green thread or async systems, this can allow slow requests to continually stack up. Eventually, the container will run out of resources and get killed, dropping every request it had in progress. Infinite scaling can sound good, but even low overhead systems will eventually hit hard limits. And speaking of memory limits, out-of-memory errors are a lot more common in container environments. This is not unexpected, since increased density and resource utilization is often an explicit goal of moving to containers, but it does create some new challenges. These limits are implemented at the cgroup level, so it adds up all the subprocesses inside the container. When the limit is hit, the process with the highest usage will be stopped. Most container systems include some form of last restart reason to help track down the source of OM events, but because of how process signaling works in Linux, this can only record when PID 1 inside the container is terminated. If a subprocess gets zapped, that's invisible to the container system, and your web server would have to handle it, and most do not. As a specific example, Junicore doesn't even log a warning when this happens. If we can keep everything inside a single process in our container, it makes monitoring administration a whole lot easier. One thing that can bloat the memory usage of process-based servers in particular is the interaction between Linux copy-on-write memory and Python's reference counting. All Python objects have a reference count in their object header, used to track when the garbage collector can get rid of an unused object. When a process forked, everything in memory has to be copied for the new process being created. But Linux is sneaky. Rather than copy them all up front, which would take a long time, it leaves them as a reference to the original. If either the original or new process write to a chunk of memory, that particular chunk will be duplicated so that each copy gets its own. This is great for efficiency, since it means that a forked copy uses a fraction of the memory of the original and can be started a lot faster, but then ref counts kind of mess everything up. Updating the ref counts on all kinds of global objects like classes and modules mean that those pages get written to and they have to be duplicated. Python 3.7 did add a gc.freeze function to lock ref counts, which can be called right before forking and might help with efficiency, but it's relatively new and hasn't been thoroughly battle tested. While it's not specifically tied to containers, Prometheus is especially common in the container world for gathering both system and application metrics. For some complicated architectural reasons, the Prometheus client library exposes each metric being collected as a global variable. All these globals get exposed via an embedded HTTP server hidden in a background thread, and Prometheus scrapes that server to get all of the data into the time series database. This works as expected with threads and with green threads, but a variable can't be shared between subprocesses. Because multiprocess workers are so common in Python, the client library does have some handling for them using mmapped files under the hood, but it's relatively fragile and it's nice to avoid needing. I mentioned a while back that green threads and async code have this fail dangerous risk. This happens when your application code makes a call outside the scope of the green thread or async library. For gthread or eventlet, this would mean calling a blocking function that isn't monkey patched, or for async IO, it would mean calling any non-async blocking function. In either case, the main thread is stuck waiting for that call to finish so that it can resume running tasks. Both of these can be avoided with careful code review, but I say it fails dangerous as opposed to fail safe because it only takes one errant commit to bring your throughput crashing down, and these bugs can be really hard to catch in tests where concurrency isn't a factor. Now I get to put on my opinionated hat. Those 5 issues combined make a strong case for deploying Python applications containers using a single process with thread-based workers. We have multiple replicas for redundancy and concurrency, but this gives us good backpressure behavior, dodges problems with memory limits and efficiency, integrates well with container ecosystem tooling, and limits the effect of concurrency bugs. What's not to love? You might have guessed that this talk was going to be about threading, or the GIL wouldn't have really been an issue, but now that we're full steam ahead for a threaded server, let's think about the kind of code that runs in a modern web app. On the web side, we don't usually have much CPU-intensive code. Almost all of the time in web handlers is going to be spent blocking on a socket, either waiting for a database query response or for some JSON from an HTTP API to come back. The JSON parsing itself can actually be a CPU hotspot, and notably the standard library JSON model does not release the GIL even when you're using the C extension, so keep an eye on that. But overall, the GIL generally has a pretty low impact on web server code. Unfortunately, CPU-bound code is much more common in queue workers, and with good reason. The whole idea of tools like Celery and Spark Streaming is to keep our web responses really fast by moving the slow parts into the background, but we do have to handle them eventually. The main things to be on the lookout for are tight loops in Python code doing some kind of computation. Just like in web code, database queries and HTTP requests will drop the GIL, and some common libraries like Pillow are careful to release the GIL during compute-heavy tasks, even if they're not doing any I/O. But Python code aggregating database results or reformatting some JSON is going to hold on to the GIL and block other tasks. Especially for SQL queries, do as much of the work in the database as you can. The convoy effect is a behavior of schedulers, where one big slow job blocks a bunch of faster ones, just like a convoy traffic jam on a highway. This can happen in queue workers, where the same server is handling many different kinds of tasks that vary in speed. This results in uneven throughput. Overall, the CPU is still always being used, but you'll see bursts of smaller tasks completing every few milliseconds as the larger tasks get preempted. If you have any C extensions, though, and they hang on to the GIL, this can be magnified many times over, as those C calls can't be interrupted by Python. Monitor your task latency and consider sharding your workers by task priority or task speed if you want to smooth things out. This is especially important in real-time streaming systems, where a slow task can also block the listener thread in addition to the other jobs. So that's all a bunch of potential problems. How do we rephrase them into solutions? Our optimal web server will run a single process and a configurable number of worker threads. Finding a web server that fits the bill is surprisingly difficult. While gUnicorn and uWSGI both support thread workers, they use a process supervision system that can't be disabled, so neither provides a true single process server. Some async servers like Hypercorn offer thread-based backwards compatibility with WSGI, but these are complicated to set up if you aren't already using ASGI for other things. The best server I've found is Twisted Web. It provides a simple threaded WSGI runtime on top of a high-performance async socket layer. To get started, you can use it directly from the command line, or you can call it from a server script for deeper customization. This also means you build on the entire Twisted networking ecosystem, including things like automatic Let's Encrypt support, deep metrics and instrumentation, and of course, native async handling if you need it later on. I've collected my tweaks and additions for things like Prometheus metrics and log handling into a small library. You can also use that directly as a command line tool to start a web server, or you could look at it for ideas on your own customizations. Worker queue servers aren't standardized like web servers, so I can't be quite as general there, but Celery in particular does support a thread worker as of version 4.4. For other tools, check their documentation and look for things like concurrency and runtime settings. Picking the right number of replicas and threads is more of an art than a science. Replicas cost more in terms of RAM, but they provide redundancy and concurrency, and threads are cheap, but using more than a few dozen of them is usually going to hit diminishing returns on performance because of the GIL. To really dial in your scaling factors, you're going to need to be monitoring your container CPU and memory usage. In Kubernetes, you can get these from the kubelet metrics, and in other systems, you can run cAdvisor yourself. If you see requests start timing out at your load balancer, but your CPU is mostly idle, adding more threads may help. If requests are timing out after reaching your web server, or if your CPU usage is nearing 1 core per container, then you probably want to either add more replicas or optimize your code. If possible, directly track the number of active worker threads on each server for more accurate analysis. I opened this with a vague question. What does the GIL mean for containers? Over the last 20 minutes, hopefully I've convinced you that the answer is not much, you just need to be careful. So to review, today we learned how the GIL works, the 4 main types of worker models in Python, that threaded servers have a lot of benefits, and some patterns for operating applications using threads and containers. And most of all, hopefully we've learned that we don't need to fear the GIL. Thank you very much.